Welcome to note set number 34, where we'll be talking about the continuous time transfer function and its relationship to the frequency response. So this follows almost step by step in sync with our same discussion of these topics for discrete time. So you might want to compare the notes in this note set to those that are the same name for discrete time. So for discrete time system, we took the difference equation and we took its z transform, and voila, we ended up with the transfer function. For continuous time system, we start with a differential equation, and we're going to do the same thing, take the Laplace transform of that. Now, again, we're assuming zero initial conditions like we did before. We're going to apply the bilinear Laplace transform, and later we'll worry about the impact of non-zero initial conditions. So we take the Laplace transform of that, and then by linearity we can pass the Laplace transform through, and we would have the Laplace transform operating on each of these terms. So the Laplace transform of y is just going to give us y of s times a0. I've factored out this y of s. Laplace transform of y dot of t, that's y dot of t is the first derivative. So when I take the Laplace transform of that, I get an s times a y of s, and I can pull the y of s out. All the way up to the nth order derivative, I'm going to get Sn times y of s, and I can pull the y of s out. And then notice what I get. I get a polynomial in S, nth order polynomial with all the coefficients out in front. Now I show a sub n explicitly here. We often normalize our systems so that a sub n is equal to 1. We can always do that, and it's often a nice thing to do that. That would obviously change all the other coefficients, get normalized. You don't just set a sub n to 1, you divide everything through by a sub n. So now we end up with something like this. We've done the same kind of thing on the right hand side, and now what we want to do is solve for y of s. So all we really have to do is take this over to the other side via division, and when we do that, voila, we've got x of s times some big thing, and that is our transfer function, because again, harking back to this is just a generalization of the idea of phasor, where x of s is playing the role of a very glorified phasor, and so the thing that multiplies the phasor is the frequency response, but now it's a more generalized thing, it's the transfer function. So all those same kinds of ideas carry through. And again, just like for the transfer function of a difference equation, for the discrete time, all we need to do is just go up here and look at these coefficients, and we can write our transfer function by inspection. So that's really nice. However, for continuous time systems, sometimes the system is a circuit, and we can write the transfer function immediately by analyzing the circuit rather than having to first find the differential equation. So that might be good news for those of you who in your circuits class struggled to write the differential equation for a circuit. You don't have to really go that route at all, as long as you can solve a circuit that has complex impedances in it. But now instead of having j omegas in it, it's going to have s. So just as a challenge to you, something for you to think about, and we'll talk about this in the class. Think about an inductor has v of t is equal to L di dt. Think about taking the Laplace transform of both of those sides and coming up with a Laplace transform version of Ohm's law, and you'll actually discover, if you do that, you'll have essentially discovered why we say the impedance of an inductor is Ls. So that's something for you to try, and we'll talk about that during the class. All we have to do is replace by S variable impedances. Then we just have to solve our circuit like we've been doing before to find the transfer function. So let's do that. We're going to take L and replace it by Ls, take the capacitor, replace it by 1 over Cs, x of t gets replaced by x of s, y of t gets replaced by y of s. And so now, even though we're still showing the schematic symbols for inductor and capacitor, what we really have is effectively like a DC circuit. We can think of it as a DC circuit with complex valued variables or elements. So now we just analyze it as if it's a bunch of weird resistors, and in this case voltage divider gets us to the output in short order, and we discover that there is this thing that multiplies x of s, and that is the transfer function. And it's always a good thing, listen carefully, always good, since we're going to be doing inverse Laplace transforms. We always want to end up with a polynomial in S over a polynomial in S over a polynomial in S. So that requires a little bit of a a little bit of algebra to get it into this ratio of two polynomials in S. And furthermore, we want to make it so that the first coefficient, the coefficient of the highest power in the denominator is 1. We can always normalize it to do that. So once we have that transfer function, whether we got it from the differential equation or whether we got it from analyzing a circuit, when we get it like this, it'll be a ratio of two polynomials. I'm showing it here in standard form. And then we can identify the numerator and the denominator polynomials. And unlike in the Z transform case, we don't have to worry about any z to the power terms sitting out in front. And we also don't have to worry about Z inverse form versus Z form. In Laplace, it's just S. We'll always end up with S's. So just like we did for discrete time transfer function, we'll say that the poles of h of s are the values on the complex S plane where the magnitude goes to infinity. And likewise, the zeros are the S plane complex values where the magnitude equals 0. So from that, we can then say we can take this numerator and denominator and factor them into their different factors by finding the roots of those two polynomials. And so the roots of the denominator polynomial determine the poles, and if we have an nth order polynomial, we'll have n poles, and the roots of the numerator polynomial determine the m zeros. This is very much like the case for the discrete time case. So now let's take a differential equation here and find the transfer function and then find its poles and zeros. So we have a third order differential equation here. So we should have 3 poles. We've got highest derivative on the right hand side is 2, so we should end up having 2 zeros. So by inspection, we can immediately write it like this. Now with a little bit of work, we can factor this. Bear in mind, MATLAB has a nice command called roots that helps you do this for the higher order polynomials, but sometimes you can factor it by hand. And so here we've factored the numerator into these two terms, and we see that it has 2 complex conjugate roots. So these roots will always show up as complex conjugate pairs. So we've got two zeros, one at -3 plus j and one at -3 minus j. In the denominator, we've got a single distinct real root and then a pair of conjugate roots. So we've got a pole at -4, and we've got a pair of conjugate poles, one at -1 plus j and one at -1 minus j. And here I'm showing that you can use the roots command. You just put the coefficients directly in here, and use this roots command to find. It doesn't make the plot for you. It just spits out what the root values are, and then you can make the plot yourself. Now, oddly, there is a z-plane command that gives you the pole zero plot for the discrete time case. There's no s-plane command in MATLAB, but you can use the roots, and then you can kind of draw the plots by hand. I'm not quite sure why that is, but it is. I suppose you could make your own s-plane command if you wanted. Just like we had for discrete time, we will introduce this concept of impulse response. I think we may have talked about this before, but the basic idea is that you put in a delta function. So remember, this thing is infinitesimally narrow and infinitely high. We put it into our continuous time LTI system with 0 initial conditions, and we get something that comes out. We call that thing h of t. We reserve that symbol h of t for the output that comes out when we put in delta of t. And we also notice that if the system is causal, there's no way it can be anything but 0 here. So that's an easy way to check for causality. And we notice that the Laplace transform of delta of t is equal to 1. We can look that up on our table. Using our frequency or our Laplace transform system result, we know that h of t is the inverse Laplace transform of h of s times the Laplace transform of the input, but that's equal to 1, so that just goes away. So we get h of t is equal to the inverse Laplace of h of s, just like we saw h of t is the inverse Fourier transform of h of omega. So what that tells us is that this impulse response forms a Laplace transform pair with the transfer function, and also forms a Fourier transform pair with the frequency response. Now, just we'll make some simplifying assumptions here just to get a feeling for this. But suppose we have a transfer function that looks like that, and suppose that the roots of our or the poles of our system are all distinct. Then when we do a partial fraction expansion and do the inverse transform of this, we'll get all these kinds of terms, and we can see that when these poles, when these roots of the denominator polynomial have negative real parts, these things are going to decay, and we'll talk more about that as we go on here. For real-world systems, we want our impulse response to decay with time, and that means all the poles have to have real parts that are less than 0. And so that leads us to this idea of stability. Again, we're not going to prove it, we're just stating it. A system is said to be stable if its output will never grow without bound for any bounded input signal. So without going into all the details, we can show that a requirement for that is that the impulse response actually decays fast enough. And from that, we can then say that the impulse response decays when all the poles are in this left half side of the plane. So this gives us a very easy way to check for stability of a system. We look, are the poles, we find the transfer function, find where the poles are they in the left half side of the plane? If they are, the system is stable. Now the zeros of the system can be anywhere. Now, don't get confused. For discrete time and continuous time, you have to keep track of which one is inside the unit circle and which one is in the left half side of the plane in order for us to have stability. So keep your eye on that. Now, just as a passing comment, if you've got a circuit and all it has in it is R's, L's, and C's, we've got no transistors, no op amps, nothing like that, then the circuit will always be stable. So when designing passive RLC circuits, we don't have to worry about stability. But as soon as you start putting amplifiers in there with transistors, op amps, and things like that, especially those with gain greater than 1, and especially if there is feedback involved, then our systems might start becoming unstable, and we have to analyze that and worry about that. Now, we've talked about the relationship between the CTFT and the Laplace transform, evaluated on the j omega axis, but only if the j omega axis is inside the region of convergence. Well, for causal systems, the j omega axis is always inside the region of convergence. For causal systems, the j omega axis is inside the region of convergence if all poles are in the left half side of the plane. So causal stable systems, we can always convert h of s into h of omega by just taking s and replacing it by j omega. So for discrete time systems, we found the frequency response in MATLAB using a command called Freq. There's another command for the continuous time case, and it's called Freq or Freqs. And you use it exactly the same way. You look at your transfer function, you grab the coefficients, you put them into numerator and denominator vectors, and then you put those into your Freqs command, and you have to tell it what frequencies you want it to evaluate, and you need to pick a specific appropriate spacing there. So that takes a little bit of judgment and insight to be able to do that. And if there's any coefficients missing up here, you're missing a power, that means that it has a 0 coefficient, and you have to account for that when you put those in. So here's a nice pretty picture, pole 0 plot on the left showing the magnitude plot of h of s over the S plane, and this picture comes from one of my favorite op-amp books. I give it credit on the next slide. And so, what we can see, very similar to what we saw for discrete time, is poles pull the surface up to infinity. So that would be these things. Here's the j omega axis, here's the sigma axis, and then zeros tack it down to the ground. So I think they should have called them poles and stakes, but they call them poles and zeros. Now, for a system that's stable, causal system that's stable, the j omega axis is in the region of convergence, and so what we can do is, going back to the previous page, what we can do is slice through here. So if we imagine cutting that with a knife and then looking in from the side, that's what we would see. That is the frequency response. And so this is that same system, just showing a couple different locations for the poles. So we've cut through the j omega axis, we're looking in from the side, and this is what we would see. And what we're showing here is that when the poles are close to the j omega axis, we get pronounced peaks. As they move further from the j omega axis, we get less pronounced peaks. Same thing as for the discrete time case, except there it was closer to the unit circle or farther from the unit circle. So just keep track of all those kinds of ideas and the distinctions. So like I said, the big ideas are the same, but the details are changing just a little bit. And just like we did for Z transform, your ability to look at a pole 0 plot and figure out what the roughly what the frequency response is going to look like is a great skill to have, and vice versa. If you look at what the frequency response looks like, you should be able to at least get some rough idea of what the pole zero plot will look like, at least for very simple cases. And knowing those ins and outs is invaluable to being able to understand how to analyze systems, and even more importantly, how to design systems. This result is exactly the same as what we had for discrete time case, as well as for CTFT and DTFT. If we have a cascade of systems, it's pretty easy to show, just like we did before, that we can replace that by an equivalent system that has just a product of the frequency responses, gives us the total frequency response of the system, and a product of the transfer functions gives us the total transfer function of the system. So it's just like what we saw for discrete time. And this obviously generalizes to a cascade of n systems, just like before. So we had a diagram a lot like this one for discrete time systems, and we're just showing it here again, modified for continuous time systems. We have a differential equation rather than the difference equation. We have included a circuit diagram. We didn't really talk about these characteristic modes, so really that should be removed. I'll try to take that off in the slides before I post them, so don't worry about that. But what we did see is that we can get the impulse response either from the frequency response or the transfer function by doing inverse transforms. From the transfer function, we can get the pole zero diagram. From the pole zero diagram, we can get the transfer function up to a multiplicative constant out in front, but you can at least get the basic shape and basic idea of the transfer function. I don't show it here, but you can actually also go this way. But in reality, what you're doing is going pole zero diagram to transfer function to frequency response, is kind of, even though you may not be doing that explicitly. So this gives you a one-page summary of all the kinds of ideas that we've been talking about, and I'm not going to go through it in detail, but this slide shows in words all the different paths that you can take there. So you might want to look at that page and read through this on your own. Thanks, and we'll see you in the next video.